हेलो गाइस, वेलकम टू माय चैनल। ये एक प्रॉब्लम सॉल्व करने का वीडियो है। आज हमें जनरल ऑर्गेनिक केमिस्ट्री को कुछ प्रॉब्लम सॉल्व करने वाला हूँ। सो लेट्स स्टार्ट। इन द फर्स्ट प्रॉब्लम देयर आर टू मॉलिक्यूल्स आर गिवन। द क्वेश्चन इज द टू मॉलिक्यूल्स आर chain isomers, positional isomers, metamers and all of these. So ये दो compound को देखो. In this compound the numbering starts from here. This is your carbon number 1, this is 2, this is 3, this is 4 and this is your 5. From the priority order of the functional groups, we know the CN group, the CN functional group always in prior position than CHO. We know this. So when this is the principal functional group, then this one is the secondary functional group. So the numbering starts from here 1, 2, 3, 4, 5. This is the 5 carbon chain compounds, and in this compound the numbering starts from here. This is 1, this is 2, this is 3 and this is your 4 carbon. So in this compound there are this compound is a 4 carbon chain compound and this compound is a 5 carbon chain compounds. So in these two compounds the number of carbons in the chain are different, so these are definitely chain isomers. Okay, next problem पे देखो. The question is the charge on the given atom cannot be dispersed on other atom in which of the following compounds? Look at here. Here the lone pair on nitrogen atom. This is a positive charge. In this option the carbon is negatively charged. And definitely boron has a vacant p orbital, and in this compound the nitrogen is positively charged. So in this compound the lone pair of nitrogen comes down to neutralize the positive charge, so it can have a resonating structure like this, NH2. This is your double bond, this is your CH, this is CH3. Now in this compound nitrogen has 2 hydrogen, so 2, 3, 4, nitrogen has 4 electrons, so positive charge on nitrogen. So the positive charge on carbon is actually dispersed, is actually converted to the positive charge on nitrogen. So this positive charge is actually dispersed to nitrogen. So in this molecule the positive charge is dispersed. Okay, in this compound the negative charge means this carbon contains a lone pair, so it is negatively charged. So this lone pair can resonate with the vacant p orbital of boron, because we know boron has a vacant p orbital. Boron has 4 orbitals, 1, 2, 3, 4 orbitals, but boron contains 3 electrons in its valence shell. So boron has 1, 2 and 3 electrons, so this is a vacant p orbital of boron. So in this compound it has another resonating structure, CH2 double bond boron. This is your CH3 and this is your CH3. Now in this structure boron has 1, 2, 3 and 4 electrons. So in the valence shell of boron there are 3 electrons. Now it contains 4, so boron is negatively charged. So the negative charge on carbon is actually dispersed to the orbitals of boron. So charge dispersion occurs here, charge dispersion occurs here. But in this compound, look at here, these things can't possible. This is not possible anyway. You can't write in this way. I just write it. ये देखो, double bond, NH3, nitrogen is positive, or whatever be the charge of nitrogen. Look at here, this structure can't be formed. There is no existence of this structure. Question is why? Because nitrogen has 4 orbitals. In the valence shell of nitrogen, there are 2 s orbitals and 2 p orbitals. We know s orbital, s subshell has 1 orbital and p subshell has 3 orbitals. So there are 4 orbitals are there. 4 orbitals of nitrogen. There are 4 orbitals of nitrogen, but in this structure nitrogen contains 1, 2 and 3, 5 electrons. So 5 that is 5 pair of electrons, that is 10 electrons. So the 10 electrons can't be accommodated in the 4 orbitals of nitrogen. So this structure of nitrogen, this structure is not has no existence. That is, nitrogen can't have 5 covalent bonds. Nitrogen can't expand its valency beyond 4, covalency beyond 4. So this positive charge can't be dispersed here. This is not possible. So this is your answer. The positive charge on nitrogen can't disperse into the benzene ring because this resonating structures has no existence. ओके आगे बढ़ते हैं. ये प्रॉब्लम पे देखो. द क्वेश्चन इज द करेक्ट ऑर्डर ऑफ स्टेबिलिटी ऑफ द गिवन कार्बोकैटायंस इज देयर आर 4 कार्बोकैटायंस आर देयर 1, 2, 3 and 4. We have to arrange these 4 carbocations in their order of stability. ये देखो, ये oxygen has 2 lone pair of electrons. So this lone pair of electrons can donate in this way. It can resonate in this way. It can have a resonating structure. So this carbocation is stabilized by the resonating effect, by the plus resonating effect, plus R effect of the oxygen, of the adjacent oxygen. In this structure, this lone pair is involved in resonance. So this oxygen can also show plus R effect, which stabilizes the carbocation. But in the carbocation 2 and 3, there is no such resonance effect of oxygen. Oxygen has no resonance effect here because there is no adjacent carbocation, and oxygen has no resonance effect also here because it has no adjacent carbocation. So definitely carbocation 1 and 4 are more stable than 2 and 3. कार्बोकैटायन 1 और 4 के बीच देखो, in carbocation 1 there is 1 alpha hydrogen. This is your alpha carbon, and this alpha carbon contains 1 alpha hydrogen because 1 hydrogen is there definitely. So there is 1 alpha hydrogen only. But in this carbocation, look at here, there are 2 alpha hydrogens. So this carbocation contains 2 alpha hydrogen. Greater number of alpha hydrogen की वजह से उस कंपाउंड पे स्टेबिलिटी इस कंपाउंड से ज़्यादा है. कंपाउंड 2 and 3 के बीच देखो, this carbocations contains, this is your alpha carbon, this is your alpha carbon, and again this is your alpha carbon. So 3 and 3, 6 and 2, 8. There are 8 alpha hydrogen. So there are 8 alpha hydrogen. These alpha hydrogens are involved in hyperconjugation. In this carbocation, this is alpha carbon, this is alpha carbon. Here it is contains 3, here it is contains 1. So there are 4 alpha hydrogen. So there are 4 hyperconjugated structures are possible for these carbocations. So between 2 and 3, definitely second carbocation is more stable than 3. So the stability order is, the carbocation 4 is more stable than 1, we can write carbocation 4 is more stable than 1, and between 2 and 3 2 is more stable, and 2 and 3 का stability definitely 1 and 4 के 4 से कम है. So the stability what is 4 is greater than 1, greater than 2 is greater than 3. So this is the order of stability, and so this option is correct. 4 1 2 3, 4 1 2 3. Okay, next problem पे देखो. This is a very important one. In the given compound, the correct order of reactivity of the hydrogen atoms towards the free radical substitution is. Look at here. There are 6 types of hydrogen. This is hydrogen type 1. This is 2, 3, 4, 5, and 6. Now we have to arrange these 6 hydrogen atoms in the order of reactivity towards free radical substitution reaction. ये देखो, अगर ये कंपाउंड पे हर कार्बन हाइड्रोजन बॉन्ड टूट जाएगा तो हमको पास ये तरह एक फ्री रेडिकल फॉर्म हो जाएगा. यहाँ पे देखो, इस कार्बन हाइड्रोजन बॉन्ड टूट जाएगा तो हमको पास ये तरह एक फ्री रेडिकल है. ये कार्बन हाइड्रोजन बॉन्ड टूट जाएगा तो हमको पास ये फ्री रेडिकल है. ये बॉन्ड टूटेगा तो हमको पास ये फ्री रेडिकल है. ये बॉन्ड टूट जाएगा तो हमको पास ये फ्री रेडिकल है. ये बॉन्ड टूटेगा तो इस फ्री रेडिकल विल बी फॉर्म्ड, और ये बॉन्ड टूट जाएगा तो इस फ्री रेडिकल फॉर्म हो जाएगा. Now we have to consider the stability of all of these free radicals. Look at here. But importantly, all of these free radicals will not form simultaneously. We have to consider all the free radicals one by one. Now, first of all, if this free radical is formed, all the other atoms are intact. This free radical, look at here, this is the most stable free radical because this free radical is involved in resonance over here, involving this double bond. And again, this free radical is 3-degree free radical. So the plus I effect of all these groups are there, and definitely alpha hydrogens are there. Alpha, this is the alpha carbon with respect to the free radical. This is alpha carbon with respect to the free radical. This is alpha carbon with respect to the free radical. But this alpha hydrogen will not involved in hyperconjugation because in ring structure this type of bond formation is not possible, because then the carbon becomes sp hybridized, which is not possible in the ring structure. So actually here 3 and here is 2 though, so actually the 5 alpha hydrogens can be involved in the hyperconjugation to stabilize this free radical. So this is a very stable free radical involving the hyperconjugation involving the 5 alpha hydrogen, and also by resonance involving this double bond. So this is the most stable free radical. So this carbon hydrogen bond will be the most weakest bond, because after the removal of this hydrogen atom from here, this free radical will be very stable. So this bond will be very weak, and this hydrogen will be the most reactive hydrogen atom. So the number 2 hydrogen is the most reactive one. We can write here number 2 hydrogen is most reactive. Next, we consider another allylic hydrogen atom here. Next, we have to consider the free radical over here. We have to consider the free radical over here. If this bond is broken, the free radical will be formed here. Again, this free radical is involved in resonance involving this double bond. So this is the allylic position with respect to the double bond. This is again allylic position with respect to the double bond, but this free radical is 3 degree, that was 3 degree. Now this free radical is 2 degree. So there are 2 alpha hydrogens, alpha carbon is there are 2 alpha hydrogens. So this 2 alpha hydrogen will stabilize the free radical, and this resonance will stabilize the free radical. But its stability, this free radical से definitely कम हो जाएगा. So this hydrogen is next reactive hydrogen. So 2 is more reactive than 4. Now after 4, look at here. If free radical is formed here, if free radical is formed here or here, we can compare between these 2 free radicals. When this free radical will be formed, then there will be, this is your alpha carbon, this is your alpha carbon. So there will be 1 and 2, there will be 3 alpha hydrogens with respect to the 6 hydrogen, the hydrogen assigned as number 6. So there are 3 alpha hydrogen, and if free radical is formed here, there will be 2 and 2, there is 4 alpha hydrogens. So there will be 4 alpha hydrogens. So this free radical is more stable than this one. Both of them are 2 degree free radicals. This is 2 degree carbon, this is again 2 degree carbon, these 2 are 2 degree carbons, but this free radical is more stable than this one because it contains 4 alpha hydrogen. So the reactivity order is 2 is 4 is greater than definitely 5, greater than 6. Now what about free radical 1 and 3? Okay, look at here. When this bond will be broken, this free radical will be formed. Now obviously this is a 1 degree free radical which is not so stable, but if this carbon hydrogen bond be broken, then this free radical will be formed. Definitely this is vinylic free radical. This carbon is sp2 hybridized, and sp2 hybridized carbon is more electronegative than sp3. This carbon is sp3 hybridized, and this carbon is sp2 hybridized. So sp2 hybridized carbon is more electronegative than sp3. So sp2 carbon can't be electronically deficient, but because when free radical is formed, the carbon becomes electronically deficient, because any free radical, any sort of free radical, in any free radical the carbon contains 7 electrons in its outermost shell. Carbon has 3 covalent bonds, 3 into 2 6 plus 1 7 electrons. So all free radicals are electronically deficient. So when free radicals is present at the sp2 carbon, this is more electronegative carbon, so this free radical will be most unstable. So this sp3 free radical, although it is 1 degree free radical, this is more stable than sp2, the vinylic free radical. So definitely the 1 hydrogen is more reactive in comparison to hydrogen 3. So the reactivity order of hydrogen atoms will be definitely here. This option is given in option B, so B is your correct answer. if the question will be such that the stability order of this carbon hydrogen bonds, so definitely the order will be reversed, because this carbon hydrogen bond is most stable. So the stability order, I can write the stability order or the order of strength, I can write the order of strength of the carbon hydrogen bonds. The order of bond strength, the order of bond energy of the carbon hydrogen bonds. Then the order will be 3 is the most stable carbon hydrogen bond. The bond with the hydrogen atom assigned as 3 with this carbon. This is the this is the strongest bond, carbon hydrogen bond. Then 1, then 6, then 5, then 4, then 2. Definitely this will be the order. Okay, आगे बढ़ते हैं. Now problem 5 पे देखो. In question number 5, which of the following is the correct order of reactivity of chlorides for the given compounds? There are 5 compounds given. Compound 1, 2, 3, 4 and 5. We have to arrange these 5 compounds in the order of reactivity. All of them are chlorides, definitely. Now look at here. If we remove the Cl minus atoms from here, from all of these compounds, we have, if we remove Cl minus from compound 1, we will get this carbocation, this one. If we remove Cl minus from here, we will get this carbocation. If we remove Cl minus from here, in this way, you will get this compound, this carbocation, this one. If we remove Cl minus from here, we will get this carbocation. By removing Cl minus from here, we will have this carbocation, and after removing Cl minus from here, we will find this carbocation. Now we have to arrange these 5 carbocations in the order of their stability. Now look at here. This is an aromatic carbocation. This is a resonance stabilized system. It contains 2, 2 and 4 and 2, 6. That is 6 pi electrons. We know according to Huckel's rule, there are the system contains 4n plus 2 number of pi electrons. Cyclic, planar and conjugated systems are known as aromatic compounds. So this is an aromatic system. Again, there are 2 pi electrons, so this is again an aromatic system. So this is an aromatic system. This is again an aromatic system. So the stability of aromatic systems are definitely greater than the other. So this carbocation is the most stable, because between these two, this is more resonance stabilized. The resonance stabilization energy is greater in this compound than this one. This is also resonance stabilized, but this one is more, it has more double bonds, so it is more conjugated system. Its resonance energy is greater than this one. So this is the most stable carbocation. So we can arrange in this way. The carbocation 1 is more stable than 3. Now Between 2, 4 and 5, this is an allylic system. There is also resonance, but this stability is much less than that of the aromatic system. So next comes the compound number 4. Then there is no, this is a standard compound. It has this is a 2 degree carbocation. It has only some plus I effect or maybe hyperconjugation. There is alpha carbon, there is alpha carbon. So there are 4 alpha hydrogens. 4 hyperconjugated structure will stabilize this carbocation. So it is somewhat more stable than this system because it contains 4 pi electrons. This is an anti-aromatic system. This is an anti-aromatic system. We know anti-aromatic systems are least stable and aromatic systems are more stable. So the stability order will be 1 is more stable than 3, then comes compound 4, then it is 5, and lastly compound 2. So the stability 1, 3, 4, 5 and 2. So this one is the correct option. This is the order of reactivity of the given compounds. So this is all about today's lesson. Thanks for watching the video. Thanks a lot.